Hello everyone, I'm Chen Feng, a PhD student at the Visual Information Lab from University of Bristol. I would like to present our paper, RankDVQA, Deep VQA based on ranking-inspired hybrid training. The work was created together with my colleague Duolikun Danier and our supervisors, Dr. Feng and Professor David Bull. Here is a quick review about RankDVQA. We proposed a new two-stage training methodology using ranking-inspired loss functions. We developed a large-scale VQA training database with reliable quality labels without performing costly subjective tests. We trained a transformer-based network for patch-level VQA and then employed multiple small video databases to train an aggregation network for spatio-temporal pooling to obtain sequence-level quality indices. This figure shows the performance of the proposed metrics and selected benchmark VQA method. Both full reference and no reference RankDVQA achieved the best performance in each category. In recent years, deep learning has driven the development of video quality assessment methods, achieving promising results compared to the conventional approaches. As a showed high-level framework, deep VQA normally extracts and processes the features of the video patches, and then obtains the sequence-level quality index through the aggregation of the patch-level quality indices, such as deep VQA, LPIPs, and C3DVQA. However, deep VQA methods tend to be limited by the following issues. The problem one is the lack of reliable, large, and diverse training databases. The most existing method was trained using a relatively small video database, typically with only a few hundred subjective labels, because the subjective test is time and costly consuming. This is insufficient for training a model with a relatively high network capacity. This is why most existing deep VQA methods only perform well when cross-validated on a single database, and show unsatisfactory cross-datasite standardization ability. The problem two is ineffective training method. The existing training process or designs only consider one distorted content each time. Meanwhile, deep VQA methods just minimize the distance between the patch level and the sequence level quality indices from the ground truth. And in contrast, the ability of a metric to differentiate the quality of differently distorted versions is an important characteristic of the VQA method that has not yet been exploited, named the ranking ability. To address the problem one, we propose a new two-stage training methodology. This first step uses VMAF-based quality ranking information to train a deep VQA model. This enables us to develop a large-scale training dataset for optimizing patch-level VQA without performing costly subjective tests. VMAF was used due to its consistent correlation with subjective ground truth, and then employs multiple small video quality databases to train an aggregation network for spatio-temporal pooling. By using this new training framework, the proposed deep VQA method can achieve significantly improved model generalization and avoid the need to perform intra-database cross-validation. For the problem two, we're utilizing the ranking information rather than absolute values of the VMAF or subjective scores. During the training process, we take two distorted sequences each time. Let's reformulate VQA as differentiating the quality between the two distorted videos. It makes it meaningful to use VMAF as a training target, allowing using a large training database. Ranking-inspired training allows the use of multiple subjective databases for joint training with different viewing conditions and score scaling. The architecture of RankDVQA is shown here. Based on the new training methodology, we have trained a full reference and no reference deep VQA method, employing a transformer-based architecture for stage 1 and 3D CNN-based aggregation network for stage 2. I will explain each stage of this in next few slides. In the stage 1, we developed a transformer-based PQA net for patch-level quality assessment. The input includes a distorted and reference patches, PD and PR with a resolution 256 by 256 in 3 channels and 12 frames. The output is quality index of this distorted patch. We employed a pyramid network for feature extraction and a spatio-temporal module for quality estimation. Here is the multiple scale quality weighting according to the extract features. For the training material and the strategy of the Stage 1, we take 230 sources video from the BVI-DVC and click. We employ 4 most popular video codec with 4 different quantization level and 4 resolution adaptations. This results a total of 14,720 distorted sequences. During the training progress, we take 2 pairs of the patches to output the product quality indices Q patch A and Q patch B. We first calculate a probability P using the product quality indices Q patch A, Q patch B with a single mode function. We progress the probability P and the Vmath difference after binarization Vmath B by binary cross entropy loss as the Stage 1 loss function. In Stage 2, we designed a spatio-temporal aggregation network STA-NET, which accepted both patch-level score tensors and the distorted feature maps extracted from Stage 1 to obtain the final sequence-level quality score. Distorted feature maps are used to weight the patch-level quality indices. In Stage 2, we employ a similar ranking-inspired training strategy rather than simply minimizing the difference between product quality and the subjective score, which allowing multiple subjective quality databases for joint training. The training databases are Vmath Plus and IVP due to their various video content. It takes 2 videos each time in the training progress. The input is 2 sets of quality indices and the feature maps generated by Stage 1. Target is normalized subjective score SX and SY. A total of 16,000 sequences pairs from the both databases, and the loss of STA-NET is ranking inspired shown here. To evaluate the performance of the proposed methods, 8 video quality datasets were employed. Result intra-database cross-validation. Both full reference and no reference RankDVQA are tested. For no reference, reference patches are not included as input. We tested 10 full reference and 6 no reference quality metrics as benchmarks shown here. The results in the table shows the full reference RankDVQA achieves the highest overall stroke value of the 0.8972 across 8 databases. The second best performer is Vmath. Based on the F-test results, their performance differences is significant on the BVI-HD and MCLV databases. In terms of complexity, the runtime of the full reference RankDVQA is 3.88 times lower than the Vmath, similar to the underperforming deep full reference VQA method, deep VQA. In the no-reference case, RankDVQA also offers the best overall performance with an average stroke of 0.7791. This figure is much higher than that of the second best quality metric JSTVQA stroke equal to 0.704. We also conducted an ablation study on ranking-inspired training method and the training framework. From the results of the ablation study, each of these made contribution to the final results. There are some visual examples. For the same source frames on the left, the distorted video A is given a higher subjective quality score than video B, and the RankDVQA correctly predicts this. Similarity for the different sources frames on the right, although distorted video B shows the less visual distortion from its reference compared to the distorted between the distorted video A and reference A. Vmath fails to predict the correct quality ranking. The proposed method does. In this work, we propose a new 2-stage training methodology for deep VQA with ranking-inspired loss functions. We introduce a large-scale training database with reliable quality labels to optimize patch-level deep VQA. We train an aggregation network for spatial-temporal pooling to obtain sequence-level quality indices. To the best of our knowledge, the proposed full reference quality metric is the first that consistently outperforms Vmath on various video quality databases without retraining. The proposed method, full reference and no reference RankDVQA, achieves state-of-the-art VQA performance. Future work should focus on more sophisticated network architectures for spatial-temporal pooling and complexity reduction for multiple low-level version tasks. I really want to thank my colleague, Mr. Duolikun Daniel, and appreciate my supervisors, Dr. Feng Zhang and Professor David Bu. Many thanks. Here is references. Thank you.